Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1822 publication of Augustin Louis Cauchy's Cours d'analyse de l'école, where polytechnique represents a singular moment in the intellectual history of mathematics, an inflection point where the foundational principles of calculus underwent a profound and deliberate reconstruction. Conceived as a textbook for the brilliant and ambitious students of one of Europe's premier scientific institutions, its purpose was explicitly didactic, yet this pedagogical mission became the vehicle for a revolution. Cauchy's work advanced a programme to rebuild the edifice of mathematical analysis upon what he perceived as the unshakable bedrock of algebraic generality, systematically expelling the appeals to geometric intuition and the ambiguous language of infinitesimals that had characterized the preceding century of discovery. This essay will undertake a direct and critical evaluation of the central claims, methods and arguments presented within the Cours d'analyse, proceeding section by section through its major conceptual innovations. We will explore the precise nature of Cauchy's proposed rigor, assessing the internal coherence of his definitions and the logical integrity of his proofs, thereby examining the work on its own terms as a foundational document that sought to bring a new standard of clarity to the Section 1, the inaugural argument for algebraic purity, the introduction to the Cours d'analyse functions as a philosophical manifesto, declaring Cauchy's central intellectual commitment. He states his intention to imbue analysis with the rigor he sees exemplified in geometry, a statement carrying a certain historical irony, as his method involves the systemic replacement of geometric reasoning with algebraic formalism. The core claim is that concepts like the infinitely small, which had fueled the developments of Leibniz and Euler, lack the necessary clarity for secure proof. His proposed alternative is to found all of analysis upon the concept of the limit. This claim of superior rigor through algebraic means is a powerful one. An evaluation of this prefatory argument reveals a deliberate and programmatic mind. Cauchy asserts that phrases such as the speed of a body at a given instant or arguments from the motion of points along curves are metaphysical constructs that obscure the true, arithmetical nature of derivatives and integrals. He presents his project as one of purification. The evidence he marshals is primarily rhetorical, an appeal to a shared desire for certainty among mathematicians. In assessing this claim, one recognizes its immense polemical power. It establishes a new criterion for what constitutes an acceptable mathematical argument. The success of this claim is measurable by the degree to which subsequent analysis adopted its vocabulary. The evaluation, however, must also acknowledge what this new program entails a shift in the very subject matter of analysis, from the study of dynamically changing quantities to the formal properties of functions and sequences defined by algebraic rules. Section 2, the limit, as the foundational construct in the preliminary chapters. Cauchy operationalizes his philosophical program by introducing the work's foundational technical definition, the limit. He claims to provide a clear and unambiguous articulation of this concept. While a variable quantity successively assumes values that approach a fixed value so as to end by differing from it by as little as one desires, this fixed value is called the limit of all the others. This verbal formulation is the ancestor of the modern epsilon delta definition. Its central claim is that it provides a complete and sufficient basis for all that follows. Evaluating this, we see its revolutionary character. The definition is purely arithmetical. It concerns the relationship between quantities and their differences. The mechanism it provides is one of comparison. It allows a mathematician to test whether a given value is a limit by examining the behavior of the difference between the variable and the proposed limit. The evidence for its utility is the entirety of the book that follows. Yet, a critical look at the claim of its conceptual completeness reveals its specific historical position. Cauchy's definition describes the behavior of a limit. It presumes the existence of the number line and the quantities that inhabit it. The definition is operational, telling one how to verify a limit, but it is silent on the ontological status of the numbers themselves. This silence is what later mathematicians like Karl Weierstrass and Richard Dedekind would seek to fill. Cauchy's claim to have resolved the foundational issues of analysis is, from a later vantage point, a claim to have successfully established a powerful and coherent framework for calculation and proof, one that bracketed deeper questions about the nature of the real number continuum. Section 3, the algebraic formalization of series, Chapter V, dedicated to convergent and divergent series, represents the apotheosis of Cauchy's limit-based program. His central claim here is that the concept of the sum of an infinite series can be made rigorous only by defining it as the limit of the sequence of its partial sums as the number of terms increases indefinitely. If this limit exists and is finite, the series is termed convergent. The single definitional move transforms the study of series from a field of often inspired but sometimes scurrilous formal manipulation into a subject of rigorous proof. Cauchy then introduces a series of powerful mechanisms for testing this convergence criterion. He presents what is now known as the Cauchy criterion for convergence, stating that a series converges if and only if the absolute values of the sums of terms from the index n plus 1 to the index n plus k can be made arbitrarily small for any k, provided n is sufficiently large. His claim is that this algebraic condition is a definitive test. Furthermore, he offers specific tools like the root test, which examines the limit superior of the nth root of the absolute value of the nth term. If this limit is less than 1, the series converges. Evaluating these claims, we find an extraordinary elevation of technical power. The evidence for their validity lies in the algebraic proofs he provides, which rely solely on his definition of a limit and the properties of inequalities. The methodology is a model of the new rigor from a clear definition. He deduces theorems that serve as practical, calculable tools. The critique of these sections is subtle. Cauchy's work on series was so successful that it revealed new problems. He famously, and incorrectly, claimed in a later section that the limit of a convergent series of continuous functions is itself continuous. The discovery of a counterexample by Niels Henrik Abel exposed that Cauchy's framework, while powerful, required the additional concept of uniform convergence to handle such theorems correctly. The claims of Chapter V are ancillary coherent and transformative, yet they also demarcate the boundaries of his innate system, opening new avenues of inquiry. Section 4, the articulation of functional continuity. Chapter VI introduces Cauchy's celebrated definition of continuity, another cornerstone of his analytical structure. The central claim is that the intuitive idea of an unbroken curve can be captured in a precise, algebraic statement about the behavior of a function. He states that a function, f of x, is continuous between two assigned limits of the variable x if, for each value of x within these limits, the numerical value of the difference between f of x plus alpha and f of x decreases indefinitely with the value of alpha. This is, again, a limit-based definition expressed in words. It claims to provide an objective criterion for a property previously understood through visual or kinetic intuition. The mechanism is again comparison. One examines the change in the function's output in response to a small change in its input. If the output change can be made arbitrarily small, the function behaves continuously at that point. Evaluating this claim, we must acknowledge its profound impact. This definition allowed mathematicians for the first time to prove, with algebraic certainty, that a given function was continuous over an interval. It shifted the discourse from discussing continuous curves to analyzing continuous functions, a crucial conceptual abstraction. The evidence for its power is demonstrated immediately in his subsequent proofs, where this definition becomes the engine of the argument. It provided the necessary tool to begin building a rigorous theory of real functions, laying the groundwork for understanding integration and differentiation as formal operations on these defined objects. The definition itself is a masterpiece of the new paradigm, a testament to the power of the limit concept to translate an intuitive idea into a workable, formal definition. Section 5. An examination of implicit assumptions. In the intermediate value theorem following his definition of continuity, Cauchy presents a proof of what is now called the intermediate value theorem. The theorem claims that a continuous function f of x takes on values f of a and f of b at the endpoints of an interval from a to b must take on every value between f of a and f of b at some point within that interval. Cauchy's claim is that his proof, based on his new definitions of continuity and limits, provides a rigorous demonstration of this fact, free from geometric appeals. His proof method is a brilliant application of the bisection algorithm. He repeatedly subdivides the interval and, at each step, selects the subinterval whose endpoints are function values that still bracket the intermediate value. This process generates a sequence of nested intervals whose lengths approach 0. He then asserts that this sequence of endpoints converges to a specific point, c, within the original interval, and that the value of the function at c, f of c, must be the desired intermediate value. A deep evaluation of this specific claim reveals a subtle but profound logical lacuna. The proof's entire structure rests on the assertion that the sequence of endpoints, constructed algorithmically, must converge to a point that is itself a number within the system. Cauchy's framework lacks an explicit axiom guaranteeing this. His reasoning implicitly assumes the completeness of the real number line. It assumes that every sequence that ought to converge like a sequence of nested interval endpoints actually has a limit within the set of real numbers. This property was not formalized until the later work of Weierstrass and Dedekind. Thus, Cauchy's claim to have provided a proof based solely on his stated preliminary principles is wanting. The proof is compelling and its strategy is sound, but its logical foundation rests on an unstated and unproven property of the number system itself. This particular failure is perhaps more instructive than many of his successes, for it demonstrates that rigor is itself a moving target. Cauchy's work pushed the boundary of certainty so far that it made visible the next, deeper layer of foundational questions. Section 6. The systematic introduction of the imaginary, a significant portion of the Cours d'analyse, is dedicated to what Cauchy terms imaginary expressions, a systematic development of the algebra of complex numbers. His claim in these sections is that these expressions, of the form a plus b times the square root of -1, while lacking a direct real-world correspondence, can be manipulated with the same algebraic rigor as real quantities. He presents them as symbolic or formal objects, defining their addition, multiplication and other operations through consistent rules. The framework he develops shows that these symbolic expressions obey the familiar laws of arithmetic. He then extends the concepts of functions, series, and convergence to these imaginary quantities. An evaluation of this part of the work shows a pragmatic and operational genius. Cauchy does not spend time on the metaphysical status of the square root of -1. Instead, he claims that as long as calculations with these symbols are governed by a coherent set of rules, they are a valid part of analysis. The evidence for this claim is the vast and consistent calculus seen as to build upon them, which forms the seed of his later, monumental contributions to complex functions. This approach, treating complex numbers as formal algebraic constructs, was a crucial step in their legitimization. It provided a secure syntax for their use, which in turn enabled the later semantic interpretations by Gauss, Argand, and others, who visualized them in the complex plane. Cauchy's claim to rigor here is fulfilled at the algebraic level, successfully incorporating them into his analytical program and demonstrating their immense utility for solving problems involving real functions and integrals. In conclusion, the Cours d'analyse stands as a work whose internal claims fundamentally reoriented the practice of mathematical analysis. Cauchy's central assertion that the subject could and should be rebuilt upon the algebraic concept of the limit was substantiated through a systematic and largely successful execution. His definitions of limits, convergence, and continuity provided a new vocabulary and a new standard of proof that became the bedrock for 19th century mathematics. Our section-by-section evaluation reveals that the work's primary claims to rigor are overwhelmingly validated within its own context. The framework is powerful, coherent, and productive. The analysis also uncovers the historical contingency of its own standards. In the proof of the intermediate value theorem, we find the limit of Cauchy's own system, a point where an unstated assumption about the nature of the real number continuum is essential for the argument's completion. This discovery, however, diminishes his achievement in no way. The enduring significance of the Cours d'analyse is precisely this dual character. It provided a powerful and functional foundation for analysis, while simultaneously illuminating the deeper foundational strata that would require the attention of the next generation of mathematical pioneers. It solved the problems of one era and, in so doing, elegantly posed the defining questions for the next.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.